Hello class. So this is the third video on section 5.3. In the previous video, we were going through this whole process of approximating the area, the net area bounded in the interval x to x plus h. Right? So we went through this whole discussion and we ended up using one rectangle approximation, seeing that we can approximate that area by h, which is just the length of that interval, and the height, which was given by f of x, using the left endpoint. From all that, we went through just a little bit of algebra and limits, and we concluded that the function f is actually an approximation for the derivative of the area function. And as we noted, if we actually had equality, then then the area function would be an antiderivative for f. And as I mentioned, that actually turns out to be true. So this is theorem 1, fundamental theorem of calculus, part 1. So this is the first part. If f is continuous on the interval AB, and remember for us, continuous is the same as integrable. And I keep stating this so that it's basically ingrained in your heads that continuous on an interval AB for us is the same as integrable on that interval, which is the same as saying that the definite integral exists. It's the same as integrable on AB, which is the same as this thing existing, right? This thing exists. The definite integral exists. Okay. So if f is continuous on the interval AB, then the area function, right, which we saw before, right, the only condition here is that since we want to focus on the interval AB, we're going to restrict the upper bound of our interval, right? So remember that the right endpoint of our interval in the area function, that's what's changing, right? So here, I don't want to change x all over the place. I want to make sure that the right endpoint of my interval is inside the interval AB. Right? So for example, I could have A here and then B here. I want to make sure that my x is between A and B. Right? So if I'm calculating net area, I'm calculating the net area on this interval here. Okay. So what does the fundamental theorem of calculus part 1 say? That the area function is continuous on AB and differentiable on the open interval AB. Right? So this function A of x, which is giving us net area, right, on the interval A to x, is continuous as a function on the whole interval AB and differentiable on the interval AB. Additionally, and this is the part that's going to be most useful for us, is that the derivative of A of x, as we saw in the previous video, was approximated by f of x. It turns out that it's exactly f of x. So it's an equality, which implies that A is an antiderivative of f on the interval AB. Again, that's the most important part. So when I try to remember this theorem, I just think, okay, I already memorized these conditions before in the mean value theorem, right? Okay, a function that's continuous on an interval and differentiable on the open interval. Okay, the area function is continuous on the interval AB and differentiable on the open interval AB. And then the next part, which is the most important part for us, okay, the derivative of the area function with respect to x, of course, is exactly f of x. Right? Hence, A is an antiderivative of f. Right? That's what an antiderivative is by definition. Okay. So that's the fundamental theorem of calculus part 1. Now, what I would recommend, and I'm going to stop here for the videos because these are the videos for Friday. What I recommend is just go back. I made sure to use as many pictures as possible so that you see that nothing crazy is going on. Everything makes sense based on the pictures, right? And then the fundamental theorem of calculus is just putting all that in mathematical notation, making it precise. Okay. So I'm going to stop here. What I'm going to show you in the next videos when I give you the videos for Monday is that this is basically the relationship we wanted. Right? Why? Because a definite integral calculates net area. It turns out that the derivative of that area function is the function f. So this is going to be exactly the relationship between definite integrals and indefinite integrals. And that's what's going to let us calculate net area or definite integrals without having to do all that something that I did at the end of section 5.2. So hopefully this gets you excited about this, because this means, oh, there's a very easy way to do this. Kind of like it's very easy to take derivatives. It turns out it's very easy to take definite integrals as well.